Welcome to the deep dive. Today, we're taking on calculus.
Calculus.
Yeah, a word that often sends shivers down people's spines, right?
Yeah, it definitely gets a bad rap.
But what if I told you it's not really about memorizing intimidating formulas? That it's more about unlocking some, well, really elegant insights into how our world works?
That's a much better way to put it.
You've shared some great source material with us, and our mission here really is to cut through the noise, reveal the core beauty, the power of this mathematical tool. We're going to unpack 5 fundamental concepts,
Just 5.
5 key ideas. And once you grasp them, calculus becomes much more understandable, maybe even surprisingly intuitive.
Exactly.
Think of this as your shortcut, to understanding what calculus is, why it exists, and what amazing things it helps us do.
That's right. We want to strip away the complexity, show how these seemingly daunting ideas like differentiation and integration, they're built on just a few elegant principles. Get ready for some genuine aha moments, hopefully. We're aiming beyond just textbook stuff here.
All right, let's do it. Let's unpack this by tackling something familiar, the area of a circle.
Okay.
Right, we all know the formula part, but have you ever stopped to wonder how? How was that figured out?
It's a good question.
I mean, a circle's got curved boundaries, not like a square or rectangle. How do you measure that curve using straight-edged square units? It feels tricky.
It is tricky, and that leads us straight to the first core concept, the infinity principle.
The infinity principle.
Okay, yeah. The real genius here isn't just about making things small. It's this kind of radical idea that we can use these imaginary tiny cuts.
Infinitesimal ones.
Exactly, infinitesimally tiny cuts to perfectly understand real-world curves. It bridges the gap, you see, between the, let's say, the messy continuous world and the precision of math.
So imagining the impossible helps understand the real. I like that.
Pretty much.
Let's use that classic example.
Yeah.
A circular pizza.
Okay, I'm hungry already.
So if you cut it into just a few big slices, right, and try to rearrange them, it's just a jumble, doesn't look like anything neat.
Yep.
But imagine cutting it into 8 slices.
Yeah.
Then 16. Then 100. Then 1,000.
Uh-huh. More and more slices.
The more slices you cut, the thinner they get, and the more that rearranged shape starts to look like, well, like a rectangle.
Exactly. And here's the mind-bending part. What happens when you imagine cutting that pizza into an infinite number of incredibly thin slices?
Infinite slices, huh?
If you then arrange them side by side, alternating, up, point down,
Right.
you get what is, mathematically speaking, a perfect rectangle.
A perfect rectangle from a circle.
Yep. And think about its dimensions. The length of this pizza rectangle, that would be half the original circumference.
Because half the slices make the top edge, half make the bottom.
Precisely. So that's 2 divided by 2, which is just par.
Okay, length is har, and the height.
The height or the breadth, that's just the radius of the original circle.
So a rectangle. Length r, height r.
And the area of a rectangle. Length times breadth.
So there's r, which is squared.
Boom! There it is.
Wow. So the big insight here isn't just about pizza, obviously.
No, sadly.
It's about realizing that even complex, curved shapes, their secrets can be unlocked by breaking them down, breaking them into an infinite number of tiny, simpler pieces. It's a totally different way of looking at things.
It really is a foundational shift.
But that idea, infinite slices,
yeah,
it still feels a bit, abstract. How do mathematicians actually use that? Infinity isn't really a number you can calculate with, is it?
That's a great question, a really important one. And it brings us right to our second core concept, tricky approximations, and this crucial idea of tends to.
Okay, tends to?
Yeah, you're right. You can't physically cut something an infinite number of times. Each slice would have 0 width. Makes no sense physically.
Right.
So this is where calculus gets clever. It's not always about exact numbers, but about values getting incredibly close to a certain point, approaching it.
Like getting closer and closer.
Exactly. When we say x tends to 2, we mean x is really, really close to 2, like 2.00001 or 1.999999, but not exactly 2.
Got it.
Same for x tends to 0, very close, but not 0 itself. And x tends to infinity means x is just getting unimaginably large, heading towards infinity, but never quite reaching it because, well, infinity isn't a destination, it's a concept.
A direction, almost.
Yeah.
It's about the limit, the edge of what's possible.
Precisely. And this tends to idea, it's vital for two big reasons. First, it lets us actually use that infinite slices idea from the pizza.
How so?
When we say infinite slices, we really mean the number of slices tends to infinity. It's a huge, huge number, maybe 10 to the power of 100 or even more.
Okay.
And because the number of slices is so enormous, the width of each slice, let's call it dx, tends to 0. It's vanishingly small.
Right.
And that is what lets us treat the tiny curved edge of each slice as if it were a straight line. Because if you zoom in enough on any smooth curve,
It looks flat, locally linear.
Exactly. Local linearity, that's the key. And second, this tends to concept helps us handle mathematical situations that would otherwise just break, like 0 divided by 0, or infinity divided by infinity.
Right, those are usually undefined.
Totally undefined. But when values only tend towards 0 or infinity, we can often use algebraic tricks and this limit concept to find a meaningful answer. It lets us resolve those ambiguities.
Okay, that makes sense. It's a way to handle the infinitely small or large without breaking the math.
You got it.
So we've talked about breaking down shapes using infinity, and this tends to idea. But shapes are often just pictures of equations.
Yeah, absolutely.
Geometry and algebra, they seem like separate things, but calculus really hinges on their connection, doesn't it?
It absolutely does. That's core concept number 3. The deep insight is that pretty much any algebraic equation can be drawn. It has a geometric face as a shape on a graph.
Like a fingerprint.
Kind of, yeah. So if we can study a complex geometric shape using these calculus tools, we're actually studying its underlying algebraic equation at the same time. Calculus gives us the power to analyze the dynamics represented by curves, not just simple lines. Think planetary orbits, economic models, population growth.
Things that change in complex ways.
Exactly. It's the bridge. It lets us mathematically interrogate shapes and the processes they represent.
Let's take a really simple equation, yx.
Okay.
If x is, say, hours you study, and y is, I don't know, pages you read, yx is a direct relationship. Plot it, you get a straight line.
Simple, clear, constant rate. Now, what about something like yx squared?
Okay, y equals x squared. Maybe x is time, and y is the distance a falling object travels, roughly speaking.
Sure. You plot that, you don't get a straight line. You get that U-shape, a parabola.
Right, because the relationship isn't constant. The distance covered increases faster over time.
Precisely. So a straight line is the picture of yx. A parabola is the picture of yxx. The big takeaway. This connection is fundamental. If we have some really complex shape on a graph representing some complicated equation,
We can use the infinity principle
and the tends to idea,
to break that shape down into tiny bits and analyze it mathematically, even if the equation itself looks scary.
that's the power.
Okay, so we can link equations and shapes, but shapes have properties, like steepness. How steep is a hill? How quickly is something changing?
Right. And that brings us neatly to core concept number 4, the idea of slope.
Slope. Rise over run. We learned that early on.
We do. For a straight line, it's easy. The slope tells you how steeply it's rising or falling, and it's the same everywhere on that line.
Constant slope, like y2x. It always goes up 2 units for every 1 unit across.
Correct. But what about curves, like our parabola, yx absurd, or something even wigglier? The steepness changes constantly.
Yeah, like driving on a hilly road.
Yeah.
The slope isn't fixed.
Exactly. So mathematically, slope is still defined as change in y divided by change in x. We often write it as Lyx delta y over delta x.
Delta meaning change in.
Right. For that constant slope graph, y2x, pick any 2x points, say x1 and x4.
Okay, change in x is 3.
And y goes from y21 to y24, 8. Change in y is 6.
So slope is yx equals 6, 3 equals 2.
And it'll be 2 no matter which 2 points you pick. But you can't do that easily on a curve.
Because the slope between 2 points is just an average over that section, right? It doesn't tell you the steepness at a specific point.
Precisely. But the slope idea is huge in the real world. Think about it. If y is distance and x is time.
Then yx, change in distance over change in time. That's speed.
Bingo. And if y is speed and x is time.
Change in speed over change in time, acceleration.
You got it. So slope is rate of change. Finding the slope is finding how fast something is changing.
Which brings us to the big problem. How do we find the slope at one specific single point on a curve, like yx at u? How steep is it right at x2?
Ugh, the million-dollar question. You can't pick 2 points anymore because any distance between them means the slope has changed.
So we need something else.
We need differentiation. That's core concept 5, part 1. Differentiation is the tool calculus gives us to find that instantaneous slope.
Instantaneous, like right now.
Exactly. When we ask for the slope at a point on a curve, we're imagining a microscopic region around that point.
Yep.
We use our tends to idea again. We imagine an infinitesimally small change in x.
That little dx you mentioned, where dx tends to 0.
That's the one. Over that tiny, tiny dx interval, the curve basically looks like a straight line. Remember local linearity? So over that tiny interval, the slope is effectively constant. We can use our slope formula, but with these tiny changes, dy divided by dx. This gives us the slope precisely at that point.
So zoom in infinitely close, the curve becomes a line, find the slope of that tiny line segment.
That's the conceptual heart of it. Let's take y-axis. We want the slope anywhere. We look at 2 points incredibly close, x and x plus dx. There's a bit of algebra involved expanding things out, but the key is remembering that dx is so small it tends to 0. So any term with dx squared or cubed, it becomes negligible, effectively 0.
Right, multiplying tiny numbers makes them even tinier.
Exactly. And when you simplify everything, you find something amazing. For yx saw, the slope dy dx turns out to be simply 2x.
Just say x, a simple formula.
A simple formula that tells you the slope anywhere on that parabola. If you want the slope at x5, it's 2 times 5, which is 10.
And at x3.
It's 2 times -3, which is -6. Steep downward slope there.
Wow, so differentiation finds the pattern of the slope.
Yes. If the original graph had a constant slope, differentiation gives you that constant number. If the graph has a variable slope, differentiation gives you a formula like 2x that describes how the slope changes.
Let's try that rocket example. Speed, time cubed, yx in the xo. Boss asks for acceleration at 3 seconds.
Okay. Acceleration is the slope of the speed time graph, so we need to differentiate yxo.
What does that give us?
Using the same process, the derivative of x of theta is 3xsos.
So the acceleration formula is 3t/ts, using t for time.
Yep. And at t equals 3 seconds.
The acceleration is 3 times 3 squared, 3 times 9 equals 27. Meters per second squared, or whatever the units are.
Perfect. Differentiation gives you the instantaneous rate of change. Incredibly powerful.
Okay, that's differentiation, finding the slope, the rate of change. What about the other big piece? Integration.
Right. Integration. Core concept 5, part 2. If differentiation is about slope, integration is essentially about finding the area under a graph, up to a certain point on the x-axis.
Area under the curve. Why is that useful?
It represents accumulation. If the graph is speed versus time, the area underneath is the total distance traveled. If the graph is rate of rainfall versus time, the area is the total rainfall accumulated.
Okay. Total accumulation.
Yeah. For simple graphs, finding area is easy. Remember y2x. A straight line through the origin. The area under that line from the origin up to some point x forms a right-angled triangle.
Okay, yeah. I can picture that.
The base of the triangle is x. The height is the y value, which is 2x. Area of a triangle is half times base times height. So 12x 2x.
That simplifies to an x header.
Exactly. So for the function y2x, the area under it up to x is given by the formula x so. If x3, the area is 3 squared, which is 9.
Okay, that works for a straight line. But what about curves? Like our y-axis parabola or y-7, finding the area under those looks much harder. No simple triangles.
It is harder. And that's where we need the infinity principle again. Same idea as the circle.
Slice it up?
Slice it up. We approximate the area under the curve by dividing it into a huge number of incredibly thin rectangles.
Stacked side by side under the curve.
You got it. Each rectangle has a tiny width, our friend dx, which tends to 0.
Okay.
The height of each tiny rectangle is just the y value of the function at that point.
So the area of one tiny rectangle, let's call it dA,
is its height y times its width, dx. So dA equals y dx.
Makes sense.
And to find the total area, what do?
We add up the areas of all those tiny rectangles.
Precisely. We sum up all the little dAs, and that summing up process for infinitely many infinitesimally small things, that's what integration is. It's represented by that elongated S symbol.
The interval sign.
Right. So the total area is the integral of y dx, y ate. And we usually specify the limits, like find the area from x0 to x5 or whatever range we care about.
Okay, so differentiation finds slope. Integration finds area by summing tiny pieces.
Yeah.
But you said there was a deeper connection.
Yes. The really mind-blowing part. The fundamental theorem of calculus, it turns out. Differentiation and integration are inverse operations.
Inverses, like addition and subtraction, or multiplication and division.
It's exactly like that. They undo each other.
Whoa.
If you take a function, integrate it, find the area formula, and then differentiate the result, you get your original function back.
Seriously?
Seriously. And conversely, if you differentiate a function, find the slope formula, and then integrate that result, you get back to the original function, plus maybe a constant, but that's a detail.
Let's test that, y2x. We integrated it and found the area formula was x second.
Correct.
Now, differentiated x sec. We found earlier that the derivative of x sec is 2x.
Hey,
Yeah.
you're back to where you started. y2x.
It works. So the derivative of the integral of y is just y.
d dx of y dx, y. That's it.
And the other way, we differentiated yx sec and got 3xx.
Uh-huh.
So if we integrated 3xx, we should
You
get...
get x back, plus that constant c, technically.
That's amazing. Why is that relationship so important?
Because often differentiation is easier than integration. Finding slopes can be more straightforward using those rules, like xn becomes nxn1.
Right.
But finding areas under complex curves by summing infinite rectangles, that can be really hard work.
I bet.
So mathematicians figured out, hey, if I know the derivative of function A is function B, then because they're inverses, the integral of function B must be function A. They differentiate lots of functions to build up tables, and then use that backwards to find integrals without having to do the infinite summing every time.
It's like a massive shortcut built into the math itself.
Exactly. A profoundly useful shortcut.
So let's wrap this up. For someone listening, what's the big picture? What does calculus fundamentally help us do?
In a nutshell, calculus is the mathematics of change and accumulation.
Change and accumulation.
Yeah, differentiation is about change, how fast things are changing. It's about the slope, the instantaneous rate.
How steep the curve is right now.
Right. And integration is about accumulation, how much stuff adds up over time or space. It's about the area under the curve, the total quantity.
Speed versus distance traveled.
Yeah.
Rate of flow versus total volume.
Perfect examples.
And the really deep insight is that these two ideas, change and accumulation, slope and area, they're not separate. They're intimately connected, two sides of the same coin.
Inverses of each other. That's the magic link.
We hope this deep dive has maybe demystified calculus a bit, helped you see past the scary formulas.
Yeah, hopefully you can grasp the core ideas now. The infinity principle, the tends to concept, the link between shapes and equations, slope, area, and that inverse relationship. It's more about these foundational concepts than just memorizing rules.
So for you, the listener, the next time you see a curve representing something changing stock prices, population growth, the path of a ball, maybe you'll think differently.
Maybe you'll think, how could I break this down? How fast is it changing at this exact moment? How much has accumulated up to this point?
This is definitely just scratched the surface, of course. It's a basic intro. But hopefully it gives you a framework, a way to think about calculus that feels less intimidating and maybe even elegant.
That's the goal, to see the elegance behind the complexity.
Thanks for joining us on The Deep Dive.